Petroff. I'm a computational chemist at PolarisQB. This how-to video covers how to access your QuaDD library of molecules for your drug design project. We will cover this topic in two parts. Part 1 concerns how to use the QuaDD dashboard to download your new 3D molecules in the protein pocket, as well as a summary of the library building process. Part 2 concerns how to explore and filter your QuaDD library. Let's get started. Okay, so here we are at the QuaDD dashboard to get our results. For this how-to video, we'll get the data from a recent Nucasine project. So to find your QuaDD library structures, we'll come over here to the dashboard, and then we'll scroll down a little bit to finished runs. And here I've typed Nucasine, so the name of our project. And then you'll see that there are a bunch of different runs, and each of the runs corresponds to a different fragmentation scheme of a reference in a particular pocket of interest. So let's look at 157 to 161, and I'll press download here. So what exactly is being downloaded? Let's take a look. So here I am in the downloads folder. We can see that I downloaded a zipped folder of the Nucasine runs. I'll click here, and we can see different folders for each of the runs. I'll click on 157. So there are several different files here. There are CSV files with raw and filtered structures. They provide an overview of these structures, including a QuaDD-generated identifier, smiles, descriptors, and any warning flags. There's also a CSV with Tanimoto scores. We also see some SDF files here. These are the 3D QuaDD-generated molecules in your pocket of interest. And before we look at the individual structures, let's look at an overview of your QuaDD library. Okay, so here we are at the QuaDD dashboard. I'll come over here to this button that says View Job Output, and we can see a summary of our library. So the first thing to do is choose your project protein. Nucasine is already here. Let's select the job run. So I'll choose 157 because that was in the set of runs that we were most interested in. And then I'll press this button and click on View New Summary. So the summary PDF is helpful for keeping track of all of the jobs that you run through QuaDD, including who did the run, so that's the user, which PDB they use, so that's the input file here. This is helpful because you often have a number of different PDB templates that you're using, such as different known binders to build out your library. And then if you scroll down a little bit more, you can look at the goals. So what was the goal for the run? Maybe you want to build a first-in-class molecule library. In this case, we wanted to do a best-in-class chemical library. If you scroll down here, you can see the fragment library type. Basically, is this a de novo library or one of our commercial libraries? And in this case, we were searching a de novo space. Here's the molecule that we used as the template. You can see that it looks pretty small, and that's because for this project, we were using QuaDD to make a ProTac, and those have to be particularly small molecules. If you scroll up a little bit, you can press this button here, and that will download all of this information as a PDF, so information about all of the runs here. So here's 157. There are two different ways of visualizing the result space, full molecule results and fragment results. So I'm going to look at full molecules first. Here's the full molecule results for the fragmentation scheme, this fragmentation scheme here. And then you can see the final full molecule similarity heat map and the full molecule property distributions here. I like to look at the fragment results as well because it shows how QuaDD used the quantum computer to build a library from the fragments. So for Nucasine 157, it used this fragmentation scheme. Stage 1 is about building and pruning the chemical space. So you can see that we got to a pretty big chemical space here. So we got to 10 to the 21st maximum raw combinations. Stage 2 is what the quantum computer did with all of these combinations in the chemical space. So in just a few seconds, the quantum computer was able to find the top combinations of R groups. Stage 3 shows the property calculations here. For this fragmentation scheme, we got to 319 molecules. Each fragmentation scheme typically produces several hundred molecules, and we recommend using a battery of fragmentation schemes and templates to build your final library. So that is how to use the QuaDD dashboard to download your new library of 3D molecules in the Protein Pocket. And now we'll move on to part 2, which is about how to explore and filter the library. The first step is to open your QuaDD library SDF files using the computational chemistry program of your choosing. We typically use our Mo license and Data Warrior, as well as other programs well suited to opening SDF files. Here is what the SDF files look like when loaded into a Mo database. And here we have an inset of the main Mo window showing a small molecule generated by QuaDD in the Protein Pocket. Here on the far left, we have QuaDD molecules, including pharmacophore score, molecule identifier, your QuaDD run, and descriptors. We can also load the SDF files into Data Warrior, as shown here. Once you have your QuaDD library open, you will notice that QuaDD runs many checks on the library and will flag potential issues. You can see the count of structure alerts on the far left and types of alerts in the following columns. So why do we leave flagged molecules in the library? One reason is that each project has different goals. Depending on where you are in your project, you may be concerned about some flags but not others, so we leave it up to the user. Another reason is that if QuaDD generates a molecule that looks great in the pocket but has one problematic group, you may want to replace that one group and then submit the molecule back to QuaDD to generate another library. We call this putting it back into the top of the hopper, and we've found successful molecules with this approach. QuaDD minimizes the ligand in the pocket, and it provides an energy calculation estimate, and we typically follow that up with additional energy calculations on a select set of molecules. For example, we often do a PBSA, which is shown here. These additional calculations help identify interesting pocket interactions, such as these protein-ligand interaction fingerprints generated by Mo. In this case, we used a de novo library, so we will synthesize the structures that we're most interested in. If you used QuaDD with one of our commercial libraries, it is possible to order the structures QuaDD suggests. That concludes this how-to video on how to download and explore your new library of molecules generated by a quantum computer. If you have questions or would like to schedule a demo, please feel free to send us an email or register at the website QuaDD.bio. Thanks.